Hello, everyone. Today we're going to finish the lectures on high-performance concrete. So this is lecture 18, high-performance concrete number 4. Okay. We'll talk about lightweight concrete, shotcrete, polymer concrete. Okay. So first of all, lightweight concrete. So lightweight concrete is concrete with air dry weight, which is the concrete has no moisture, unit weight less than 115 PCF. Okay. For normal concrete, it is around 150 PCF or 2400. Okay. So less than 150 PCF, we can call that lightweight concrete. Okay. So this is structural concrete made with lightweight aggregates. Okay, so both the sand and the coarse aggregate can be lightweight. So if both the sand and coarse aggregate are lightweight, we call that all lightweight concrete. If only coarse aggregate are lightweight, then we call that sand lightweight concrete. Okay. This type of concrete has higher strength because the sand are normal sand. Only the coarse aggregate are lightweight. Look at lightweight aggregate. For lightweight sand, has a density, the bulk density less than 70 PCF. This is close to the density of water, which is 62.4 PCF. Okay. For lightweight coarse aggregate, it is even lighter. The bulk density less than 55 PCF. Okay. But remember, this is the bulk density, including the voids between the particle. Okay. And we can see the pictures inside the lightweight aggregate. We have a lot of pores. Okay. These are synthetic lightweight aggregate made by flash. Okay. We also have natural lightweight aggregate, such as permice, scoria, or turf. Okay. So this is permice floating in water. Although there's a lot of pores inside aggregate, the pores are not interconnected. Okay. So that's why the aggregate can float on top of water. Okay. So this is particles derived from natural rocks. Also, we have man-made or synthetic manufactured lightweight aggregate produced by expanding raw materials such as flash, expanded clay, expanded shell, so on. Okay. Okay. Application of lightweight concrete compared to normal concrete. Lightweight concrete has lower density. Okay. It is main advantage, okay, because lower density means it can reduce the load on the foundation and columns and other supporting structures to about 2/3 or even less. Okay, so we can save the materials, the cross section, and also because the air are isolated inside the concrete, lightweight concrete has high thermal insulating values. Okay. So this is good for exposed structures, which may suffer from heating and cooling cycles. Okay. And also more fire resistance. The picture here shows the first interstate or center in downtown Los Angeles, which was built more than 40 years ago. Okay, this is made by lightweight concrete.
So where is the fire resistance coming from?
The fire resistance coming from a good insulation value. Okay, so not the concrete itself, but members behind the lightweight concrete. Does that make sense?
Yep.
Okay. Yeah, because just think lightweight concrete as a thermal insulator, so it can better protect anything within the lightweight concrete. So that's why we call that fire resistance, more fire resistance. But a lightweight concrete itself will be similar compared with normal concrete to resist fire. Okay, good question. Then let's look at the properties of lightweight concrete. Because the lightweight alkyd are lightweight, has lower density, sometimes even lower than the density of water, okay? Or even, of course, lower density than cement paste. So when there's a segregation problem, the alkyd tend to flow to the top surface, not to the bottom of the concrete. Okay. So that's the reason we need to limit amount of slump to increase the viscosity and increase the yield strength of concrete. Okay. And because alkyds are very porous, it may absorb a lot of mixing water. Okay. It may continue to absorb water for weeks. Okay. So because of that, some people wet alkyd before mixing. Okay. So that can very effectively reduce autogeneous shrinkage. Okay. I think we discussed that problem before, because the moisture can slowly release by the alkyd inside the concrete, so it can reduce autogeneous shrinkage. But it will be bad for freeze-thaw resistance, because saturated alkyd can also cause freeze-thaw damage if the temperature fell below zero. And alkyd has rougher surface because it has a lot of pores, especially for natural lightweight alkyd such as permites. So it makes pumping more difficult. And compared to normal concrete, it needs more cement to achieve the same strength and the same workability. Same thing, because lightweight alkyd are rough, so that will reduce workability. And also because it is porous, it will reduce the strength of concrete. So if we want lightweight concrete to be stronger, we need more cement paste, so we can afford to, for example, reduce the water cement ratio. For mechanical properties, the compressive strength is low for obvious reason. If we do not change the water cement ratio. Okay. Elastic modulus is also low because the porous alkyd are softer, okay, compared to normal alkyd. So the E value for lightweight concrete around 1/3 to 2/3 of that of normal concrete. And the shrinkage and creep are also higher. That is because we know only cement paste will shrink. Alkyd does not shrink, so alkyd will serve as restrainer for the shrinkage of cement paste. Because lightweight alkyd are softer, has lower E value, so the restraint effect from lightweight alkyd will be lower. Okay, so the cement paste will have more freedom to shrink. So that's why the shrinkage and creep are higher. The feeder mode may also change. Okay, remember where the crack generate and where the crack propagate depending on the weakest link of the three components: the cement paste, the ITZ, and alkyd. Okay. For lightweight concrete, the alkyd may be the weakest link, so the crack may generate within the alkyd. Okay. So that's the difference between lightweight concrete, normal concrete, and high strength concrete. Okay. We also have ultra lightweight concrete, which has air dry unit weight less than 70 PCF. Okay, so that's close to the density of water. The strength is lower, only around 1 KSI. Okay, so this is not structural concrete. For structural concrete, we need at least 4 KSI or 28 megapascal. Ultra lightweight concrete is mainly used for thermal insulation purpose and other non-load bearing members. If the density is between 20 to 70 PCF, sorry, I take that back. So if the concrete does not have any aggregate, okay, we call that aggregated concrete or cellular concrete. So for cellular concrete, that's no sand and no coarse aggregate. We just put aluminum powder, and because we have a lot of alkali in the cement paste, so the alkali will react with aluminum powder together with water. It will generate hydrogen gas. Okay, so that will generate a lot of air bubbles, which are isolated within the cement paste. Okay, so that's how we make aerated concrete. The density is very low, 20 to 70 PCF, very low compressive strength. Okay. Okay. And again, the air voids are not interconnected, which means if you put cellular concrete in water, it will not sink to the bottom. Okay. And it's also mainly used for non-structural thermal insulation purpose because the strength is very low and the thermal insulation value are very high. Okay. So that's lightweight concrete. Next is shotcrete. Okay, so shotcrete is a process. Okay, we use compressed air through the hose. So the compressed air will force the mortar, sometimes concrete, through the hose and nozzle onto a vertical surface, sometimes even overhead surface. Okay. So the concrete travels at very high velocity, around 50 to 200 miles per hour, and that can form a structure and sometimes non-structural component for buildings. Okay. For shotcrete, we do not need any type of formwork, so very fast to apply shotcrete. So that's one of the biggest advantage for shotcrete. Okay. Again, shotcrete is mortar or concrete. Even for concrete, the amount of coarse aggregate are lower compared to normal concrete. Okay. So shotcrete is shot into place using compressed air. Okay. So commonly made by mortar, up to 20 or 30% of coarse aggregate, and the size is also limited. Okay. The reason for that is because we pump the concrete at very high speed. If we use larger coarse aggregate, we may lose a lot of this coarse aggregate particle after the concrete shot to the surface. The procedure of applying shotcrete, first of all, we need to clean the surface, the substrate, okay, with water, using high pressure water to remove the dust and the sand, so we can ensure good bonding between the existing concrete and the shotcrete, and also ensure the shrinkage will not be too high. Okay, so we make the substrate saturated. So the surface should be saturated at least overnight before application. Otherwise, we may have too much shrinkage in the shotcrete. And wet curing is necessary to develop a strength. It should be done at least 7 days after shotcreting. Shotcrete concrete are brittle and may crack because the tensile stress due to shrinkage may be high. Okay. And also it may need a higher amount of cement for better workability because we need to pump the concrete through the holes at a very high speed. And the shrinkage could be high, up to twice the shrinkage of conventional concrete because for one, the water cement ratio will be low because the concrete need to be sticky, stick to the existing concrete. So the water cement ratio is low, shrinkage may be high. Okay. The strength of shotcrete will be high, very durable, and the permeability will also be low. So providing the concrete does not crack too much. Other properties such as density will not be much different from normal concrete. Okay. So the major advantage of shotcrete is we do not need any type of formwork. Okay. So in situations such as tunnel and reservoir lining, where setting up a formwork is very difficult, okay, we may consider using shotcrete. Okay. Very often, shotcrete also used as protective coating for structural steel, masonry, and rock. Okay. So that's the major usage for shotcrete. All right. Any questions or comments about shotcrete before we talk about polymer and concrete? Okay. So polymer can be put in concrete, and we can basically create 3 different types of polymer concrete. Okay. As you can see here, the list. The first one is called polymer concrete. Okay. The second one is called polymer Portland cement concrete. And the third one is called polymer impregnated concrete. Okay. So let's look at the definition. For polymer concrete, we do not use any water, do not use any Portland cement. Okay, so we cannot call that Portland cement. So polymer is used as the sole binding agent, just polymer with sand and coarse aggregate. Okay, so in that case, we call that polymer concrete. The second one, polymer Portland cement concrete, the polymer is used as admixtures, such as similar to superplasticizer. Okay. We also call that latex modified concrete, or LMC. The polymer, which is in liquid, sometimes in powder form, is mixed with plastic concrete. Okay. When we cast in the concrete, we add polymer as the admixture, and it will replace some of the mixing water. And the third one, okay, polymer impregnated concrete. Okay. We also call that PIC. The polymer is applied to hardened concrete by impregnating or infiltrating polymer, okay, inside the concrete. Okay. So the polymer applied in hardened concrete, hardened Portland cement concrete, not only on the surface, but deep inside the concrete to seal the pores, the capillary pores in the concrete. Okay. So again, we have 3 different types of polymer concrete. polymer concrete and latex modified concrete has been in commercial use for more than 70 years. Okay. And the polymer impregnated concrete has been used since the 70s. And we can achieve very high strengths using polymer concrete. The concrete can also set within a few hours or even a few minutes. So if we want to repair something urgently, we may consider using polymer concrete. Latex modified concrete. So latex modified concrete has very good bonding ability to existing old concrete, okay, and also very high durability to aggressive solutions. Okay. So it's mainly used for overlays in industry floors and also for rehabilitation of deteriorated bridge decks. Okay. So to protect existing concrete, and also because latex modified concrete are more expensive compared to normal Portland cement concrete, so we want to save amount of materials to only overlays. For PIC, which is polymer impregnated concrete, okay, the polymer sealing the micro cracks and also the fine capillary pores inside the concrete. Okay. So that can reduce the permeability of concrete to very, very low level. Can also enhance the strength of concrete. Okay. And PIC has been used for high strength precast concrete because in precast plant, it is easier to apply the polymer, to impregnate the polymer to concrete. It is harder in the field. Okay. So we can improve the durability of concrete members. Then let's look at each of these three polymer concrete in details. The first one, polymer concrete. Again, in this case, polymer as the sole binding agent. So we only have aggregate and polymer. There's no water and no Portland cement. And because polymer are more expensive compared to cement, so we need to minimize the amount of binder to reduce the cost. Okay. So because of that, it is very important to achieve the maximum packing density of the aggregate, okay, which means the voids between the particles will be smaller, as small as possible, so we can use as little as possible of polymer to fill the gaps between aggregate. Another important thing is we need to dry the aggregate. Okay, so this is very different from normal concrete. The aggregate need to be dried before mixing. So that is because if we have moisture on the surface of aggregate, it may cause deterioration or debonding between the polymer and aggregate. Okay. So we need to dry the aggregate, which will also increase the labor, time consuming, and increase the cost. Okay. So remember, this is for polymer concrete. For latex modified concrete, we don't need to dry aggregate, only polymer concrete. Okay, and here shows the information about the different type of formula. Okay, the strength could be very high. The setting time could be very short. Just show different type of polymer. Okay, epoxy regions. Okay, styrene, monomer, MMA, which is for mesocosaccharin, okay, acrylate, okay, with different type of admixtures. Okay, different type of binders, they may have different properties, such as the strength, the E value, okay, as we can see in future slides. Because polymer is the own binding agent in polymer concrete, so the property of polymer concrete are largely dependent on how much and the property of polymer used in concrete. Okay. For MMA, which is one type of polymer, it is brittle, okay, but we can add something else to make it less brittle. As we can see in this study, so here they use 3 different type of polymer, basically MMA with different admixtures. Okay, it's called Bhutan acrylate. Okay, by changing the percentage of Bhutan acrylate, the stress and strain curve of polymer are quite different. Okay, some of them are very brittle, such as pure MMA. Some of them are much more ductile and has much higher toughness, such as 80% MMA with 20% of Bhutan acrylate. Okay, so property of polymer concrete depending on largely depending on the property of the polymer itself. And the figure on the right compare normal concrete. This is plain and impregnated concrete, which has lower strength and also lower E value. The slope is lower compared to this is polymer impregnated concrete. But polymer impregnated concrete in this case is much more brittle, okay, compared to normal concrete. So polymer compared to Portland cement paste, it has higher strength and also has very good chemical resistance. The setting time is short, so it has higher initial strength and also higher modulus of elasticity. The usage of polymer focus on overlay and the emergency repair jobs. Okay. But the thermal and the creep property of polymer concrete are not as good as Portland cement. Okay, it is not very resistant to high temperature because that's the nature of polymer, and also the creep is also higher. Okay, so if we have a sustained load, we may reduce the level of loading, the stress level, okay, depending on how long you apply the load on concrete. And again, it may have large term deformation, okay, due to higher creep. It may relax. Okay. So for latex, so that's the first one, polymer concrete. Let's look at the next one. The second one is latex modified concrete. For latex modified concrete, we treat the polymer, the latex, as chemical admixtures. Okay, which is a colloidal suspension of polymer in water. Okay, so we treat as a chemical admixtures added to plastic concrete. Again, there's various different type of latex with different properties. So that will change the property of latex modified concrete. Okay. The latex generally has about 50% of the polymer particles, which is spherical shape, very small in size. Okay. So this is 0.01 to 1 micrometer in diameter, much smaller than Portland cement particles. These polymer particles are suspended in water together with surface active agent. And the surface active agent may tend to entrain a lot of air bubbles in concrete. So we may use air detraining agent, which is the opposite of air entraining agent. So air entraining agent is to add air bubbles in concrete to increase the freeze-thaw resistance. Air detraining agent can get rid of the air from the concrete if there's too much air. So here are more details about the latex. 10 to 25% of polymer by weight of cement is used in typical latex modified concrete. Okay. Even though we added similar to chemical admixtures, but the dosage of that is much higher. Okay, 10 to 20% of polymer. Okay. Okay. And polymer can increase the amount of mixing water, so can enhance the workability of concrete. And latex modified concrete is limited to overlays, okay, where we need high durability to resist the environmental attacks. Okay. And the latex modified concrete should made with as low additional water as possible. Okay. The purpose is to reduce the permeability of concrete, because the more water added, we have higher permeability. Okay. And the workability of latex modified concrete normally are pretty good. The typical water cement ratio for latex modified concrete around 0.4, 0.45. And the cement content is similar to normal concrete. I will see on the higher end, between 50 to 700 pounds per cubic yard of concrete. Okay. Then let's look at the curing. So the hardening of latex modified concrete takes place by drying or loss of water. Okay. So dry curing is mandatory. Okay. So this is another difference between Portland cement concrete and latex modified concrete. So we need a dry curing, not wet curing. Okay. Because the hardening takes place by drying or loss of water. Okay. Property of latex modified concrete, much higher tensile strength, because the polymer will impede or stop the crack propagation under tensile stress. So tensile strength will improve quite a lot, but not for compressive stress. Okay, so latex modified concrete does not really improve the compressive strength as significantly as tensile stress. One of the major advantage of LMC is its bonding ability to existing concrete is very high. Okay. And also it can resist the entry of water and other aggressive solutions to increase the durability. So that is because the polymer film will line in the capillary pores and also the macro cracks. So it has water and the aggressive solution. You have harder time to penetrate the concrete. Okay. So latex modified concrete is very popular materials for repair, rehabilitation of deteriorated floors, pavement, and bridge decks. Okay. So that is the second polymer concrete. And third one is PIC, a polymer impregnated concrete. Okay. Because we know the voids in concrete are responsible for lower strength and also lower durability. Okay. So if we can fill the capillary pores in concrete by polymer, we can enhance the strength and also we can enhance the durability by reducing the permeability. Okay. But how we can achieve that, especially if we have a very thick concrete members, how we can make sure the polymer can fully penetrate the concrete. For normal concrete, it is very difficult for liquid to penetrate the concrete because polymer has higher viscosity, so that will further reduce the penetrating of polymer in the concrete. So when we select what type of polymer to use, we need to select the low viscosity liquid to have better penetration. Okay. But also to dry and evacuate the concrete before subjecting the concrete to the penetration process. So that is because if the pores in existing concrete are filled with water already, okay, so the polymer cannot penetrate. So we need to dry the concrete first, and then we need to let the polymer, low viscosity polymer, to penetrate the empty pores. Okay. So we need to use low viscosity materials, such as monomer. Okay, so one example is MMA, okay, and styrene. Okay, so these are commonly used for penetration because they have a lower viscosity and also higher boiling point because we do not want to loss of these materials due to evaporation. Okay, and also the cost of these materials are lower. Okay. So we need to use the monomer to penetrate a dried concrete. Okay. After penetration, the monomer need to be polymerized. Okay, because if we just use polymer in the first place, the viscosity will be too high to penetrate deep inside the concrete. So we need to use a monomer which has lower viscosity, but after the penetration, we need to transfer the monomer into polymer. Okay, how we can do that? We have three ways. Okay. We can use the first one. We use promoter chemicals and the catalyst, which can be used at room temperature. Okay. But the process is slow and less controllable. The second way is to use radiation, such as gamma radiation. Can also be achieved at room temperature, but it may has a health hazard. Okay, you need to be very careful about radiation. So that's also make it not very popular. The third method, which is more widely used, okay, we use a monomer catalyst. Okay. Then we heat it up at 70 degrees Celsius with steam, hot water, or infrared heaters. Okay, So that can be done either on the job site or in the precast plant. Okay. So the third method is more commonly used. Then let's look at a sequence of operation. Okay. The first one is to casting the conventional concrete. That's the same as we cast normal concrete, because the quality of concrete before penetrating is not critical, because later on we need to seal the cracks and seal the capillary pores with monomer. Okay, so no special care is needed. We have limitation on the thickness of the concrete though. It should be limited to only 150 millimeter, which is only about 6 inch. Okay, because even if we increase the thickness, it is very difficult to achieve the full penetration. So then we need to cure the concrete. We can cure the concrete at ambient temperature. We need to use moisture curing at least 7 days. Okay. Again, because ultimate property of concrete does not really depend on the property of the original concrete. Okay. Sometimes thermal curing can also be used. Okay. After we get hardened concrete, we need to dry the concrete. Okay. So next step is drying and evacuation. Okay. So we can use different drying temperature. Okay. For example, if we use 105 degrees Celsius, takes 3 to 7 days. Okay. For different thickness, higher temperature, we need shorter days. Okay. But before we apply any monomer, make sure we dry the concrete totally. And the next step is we penetrate or impregnated the concrete with monomer. Okay. We can do surface ponding. Okay. Soaking the dry concrete in the polymer. And then we need to seal the polymer. Okay, because the polymer will evaporate. So to prevent evaporation, we need to seal the concrete using a steel container or layers of aluminum foil fully around the concrete. Okay. If in the field we cannot achieve the using the aluminum foil, we can cover the surface with sand, for example. Okay. And then the final step is to polymerizing the monomer, okay, using one of the 3 methods. Okay. Thermal catalytic polymerization, which use a catalyst, and also high temperature. The third method is the preferred techniques. Okay. So the time for complete polymerization take about a few to several hours, so pretty fast. After polymerization, the concrete is ready to use. Here is the major property of PIC. It has significantly improved the tensile strength and also compressive strength. Okay. So this is different from the second one, which is latex modified concrete. For latex modified concrete, only the tensile strength is greatly improved. Compressive strength, not so much. But for polymer impregnated concrete, both the tensile strength and the compressive strength can be greatly improved. And also, durability will be better. So that's the case for both, for all the 3 types of polymer concrete. including polymer concrete, latex modified concrete, and polymer impregnated concrete. Okay, so durability will be excellent. So, summary for polymer concrete: the setting time, depending on the polymer we use, typically can set within a few hours or even a few minutes. It can have very high early strength. The final strength will also be very high. Okay, again, depending on the type of the polymer. Durability will be very high due to low permeability. Okay, so that's the case for all the three types of polymer concrete. And all the three types of polymer concrete will cost much more than conventional Portland cement concrete because the cost of polymer. Okay. So that's the end for today's lecture. So we have 4 lectures from lecture number 16, I think 15, 16, 17, and 18. So we discussed different type of special concrete or high performance concrete. Okay. We're supposed to have another homework, but I think I will just skip that homework number 3, and I will let you focus on the term paper. Okay, so that's the end for today's lecture. Do you have any questions? Okay, if there's no question.